Hello geometers, this is Miss Backfish and I am here to talk to you today about rotations, one of our transformations that we can do that preserves size. So another word for that is isometry. A transformation where the size does not change is an isometry. We also sometimes call them rigid transformations. So a rotation doesn't change the size of the figure. What we're going to look at today is two things. We're going to look at just general information about rotations, and then we're also going to talk about rotations in the coordinate plane, but I want to be clear that we're only speaking today about rotations that are things that are rotated, rather, about the origin, where the center of rotation is the origin. We can rotate things about points that are not the origin. That's another video. That's actually tomorrow for us. So I just want to let you know that if you are looking to rotate a point around, or rotate a point, a figure, a line segment, whatever. If you're looking to rotate around a point that is not the origin, this is not the video that's going to show you how to do that. Okay, so first off, general information about general information about rotations, the specific transformation. In case you're confused about that, transformations are basically all of them. Transformations includes reflections, translations, rotations, and dilations. Anything that basically does something to a figure, changes it or moves it in some way. Rotations are just one of those, and they're one specific one that we're talking about today. So a rotation is a transformation that rotates, as you might expect, every point of a pre-image, remember that's the word for where we start, through a specified angle of rotation around a fixed point, meaning something that's not going to move, it's not going to rotate, a point that stays right where it is. The fixed point is called the center of rotation. And that can be anywhere. The most common place we have, we use the center of rotation is when it's at the origin, 0, 0. The degree or angle through which the pre-image is rotated to form the image, remember the image is the result, pre-image is where we start, image is where we end, is called, well, I already wrote it up here, is called the angle of rotation. All right, so if you are looking at figures like these and you're trying to decide what the angle of rotation was, the best way to do it, and let me grab a different marker here, is probably to pick one point at a time and look at what happens to that one point. Now, when we have images and pre-images, usually we use the plain capital letters for the original, which is the pre-image. And if you see that apostrophe, which reads A prime, that's the image. So if I pick a point, like for instance this point, I could have used A, shouldn't I? But let's say I use this point. I figure out where it goes on this other figure, on the result. It goes right there. So my angle of rotation, I can connect my starting point back to the center of rotation, and my ending point to the center of rotation, and then measure that angle. That would be my angle of rotation. And I didn't necessarily draw that perfectly. Sorry, it probably should have come up a little bit differently. But I can do that with any point, because all the points of the figure have to rotate by the same amount. So for instance over here, I could say I'm going to look at where this point starts and then where it ends. And that one doesn't really, it looks a little distorted, doesn't it, by the printing? And that is my angle of rotation. Okay, so as I just said, with a rotation, all points move at the same angle and in the same direction around the same center, basically is what that's saying, around the same point or center. The points on the pre-image are labeled A, B, C, and so on. The points on the image are A prime, B prime, C prime, with the number of apostrophes increasing with each rotation. And this is not something that's just true for rotations. Anytime we transform a figure, we like to, and we don't always use this, but we like to, it's kind of an easy way to see what goes together, use the primes. So my starting point might be A, my next, or my image from that first transformation would be A prime. If I do something else again, like let's say I rotate first and then I reflect, that's when you get to a double prime. If you have two apostrophes, you would call it double prime. We don't usually get beyond that. We don't usually get to 3 apostrophes, but you could. Okay, so each point in the resulting image is, okay, so that's congruent to the original. I just had to pause my video as I was making it because I thought, I'm not sure what they want me to write here. This is a worksheet by another source that I am using because I like them for the most part. But here's something I disagree with a little bit. Each point in the resulting image is congruent. Points aren't congruent because points don't have any measurement. When we talk about the word congruent, we're talking about the same length, the same angle. So that doesn't make a whole lot of sense, but that's what they wanted us to write there, so I'm going with it. And then the next one is equidistant. Equidistant, meaning equal distance from the point it corresponds to in the original pre-image. So here's how I would have probably put this, okay? The two things that we're trying to note here is that whatever angle point B rotates around my center, which is A here, that is, it's going to be the same angle for D and the same angle for C. And they're pointing out here that that angle is 180, okay? So that makes sense. If we connect A to B and A to B prime, yeah, that does look to be about 180 degrees. So just all the points that get rotated, all the vertices of whatever figure I'm rotating, will rotate by the same angle. The other thing is the distance from the point of rotation. However far it is from D to A, whoops, right there, it's going to be the same distance from D prime to A. However far it is from C to A, my center of rotation, same distance from C prime to A. So those are just the most important things for you to get from that. Not fond of using the word congruent in that context. Okay, clearly I need another page because I have some major bleed through here, don't I? Actually, before we go on, I do want to just go back and point out what would have made me a little happier with the use of the word congruent is if they had said each segment in the resulting image. And in other words, for instance, segment BD is congruent to segment B prime D prime. Or they could have said each angle in the resulting image. The angle with vertex C over here is the same size as the angle with vertex C prime over here. In other words, the big picture here is that nothing that relates to size gets changed. And that's where we can use the word isometry. Rotations are isometries. Isometry literally, and you will look at this in biology if you haven't already, iso means same. Anything with metra has to do with measure. So this is same measure. And isometry is a word that we use to describe rigid transformations, meaning ones that aren't flexible, so to speak, the ones that don't change size when they are moved. Okay, so a rigid transformation, same thing with it as an isometry, just two different ways to say it, means that whatever I'm doing to it, it's not going to change size at all. So rotations are isometries. So are reflections, and so are translations. Again, there's my one with the bleed through. We will replace it with a clean copy and move on. Now we are in the coordinate plane. What does that mean? That means on the axes, the x-axis and the y-axis. So we're plotting points. So rotations in the coordinate plane, we are strictly looking today at those that are around the origin. Okay? So notice here that these dotted lines, they go to the origin, to 0, 0, because that's our center of rotation. And when we rotate around 0, 0, usually we rotate in some multiple of 90 degrees. Okay? A quarter turn, or 2 quarter turns, or 3 quarter turns. Remember, all the way around in a circle, so all the way around through all 4 quadrants, is 360 degrees. So each quadrant, quadrant means, quad means 4, takes up 90 degrees of that 360. So we tend to do things in 90-degree increments. 90 times 2, 90 times 3, etc. Another thing I want you to notice here before we go on is that all of these are done counterclockwise. Now, I actually like to mix it up a little bit more than that, and you will have some exercises where you do mix it up, but this is a great place to start because that's the standard. When we rotate things, if for whatever reason you're not told which way to go, then you assume counterclockwise, and sometimes we use the abbreviation CCW to mean counterclockwise. So if you are told to rotate, and you're told, rotate this however many degrees around whichever point, then it doesn't tell you whether to go counterclockwise or clockwise. You assume, always assume counterclockwise, which basically means turning to the left, so to speak, the opposite way from the direction that the hands of a clock move. And just to recap something I just pointed out there are really just three things you need to know. There are three things that you need to know in order to perform a rotation. And that's really more than translations or reflections. Reflection, you just have to know which line you're reflecting over. The three things you need to know for a rotation are, I was going to turn the page over and that one's blank. Where is my center of rotation? What am I rotating around? What is my angle of rotation? How many degrees do you want me to rotate? And finally, am I going counterclockwise or clockwise? And again, if that gets left out, it's because they're assuming counterclockwise. So if it does not specifically say go clockwise, then you go counterclockwise. All right, so looking here, we have an example where a point in the first quadrant was rotated 90 degrees, so it ended up in the second quadrant. And it went from 4, 3 to negative 3, 4. Okay? What I want you to notice about this is that the original numerical value of x, 4, is now the numerical value of y. Okay? The original numerical value of y is now the numerical value of x, but not only that, it's also changed signs. So our rule, we're going to express this way. If I had more horizontal room, I would write that out in a row. So x, y, that tells me here's where I start, and it's going to end up being y and opposite of x. So the value of y does not change signs. It just moves to the first position. Moves from the second coordinate to being the first coordinate. The value of x changes signs. Remember that if I put a negative out in front like this, it doesn't mean it's going to end up negative. It does here. It means I'm going to negate it, which means it's going to change signs. If it started out negative, then it would become positive. All right, here's our rule for 180. If you look at what happens here, 4, 3 goes to negative 4, negative 3. They're in the same order, but they're both negated. So my original x and y becomes opposite of x, opposite of y, if I rotate 180 degrees. I was about to say if I rotate 180 degrees counterclockwise, but remember with 180, counterclockwise and clockwise get you to the same place. It doesn't matter if I go around this way or this way for 180, I'm going to end up in the same spot. And finally for 270, my original coordinates 4, 3, come all the way around here and end up at 3, negative 4. So the y value moved to the first position, did not change at all. The x value moved to the second position and changed. And you know what? I'm sorry. I just realized when I read that, when I said that I miswrote the rule at the top here. So I apologize for that. Let's come back up and look at that. What I just said happened, I wrote here. But look at what happened here. The x value moved to the second position, but it did not change, did it? It was the y value that changed signs up here. So we're going to mark through that and say it's negative y x. I apologize for saying that. All right, so correct that. Now I want to show you real quick a generic way to figure out where points are going to go under a rotation. All right, that we don't have to, if you forget the rules or if you don't have the rules, or if you want to apply the rules in a different situation, here is a way that we can do it. We can think of it two things. For every 90 degrees rotated, the numerical values of X and Y will trade places. Trade or swap. Okay? In other words, what I'm talking about is what happened here and down here. The order of the numbers turned into the opposite order of what it was before. Okay? So we're just talking about the numbers, ignoring the signs completely. For every 90 degrees you rotate, you're going to trade the X and Y values. Okay? Ignoring signs. So that means, for instance, if we had 270 degrees we wanted to rotate, and let's say our coordinates were this, ignoring signs completely, the first 90 would flip-flop them. So after 90, they would be in this position. Then after another 90, they jump back to where they were because they flip-flop again, they trade places again. And after another 90 degrees, they have traded back for the last time. So for every 90. So if it's just 90, then they trade. If it's 180, they trade twice, so it's like they're back where they started. If it's 270, they trade 3 times, so they end up in opposite positions from how they started. All right, so that's one way of one part. That's part one. The part two is what happens to the signs. And you basically just look at what quadrant they will end up in, or the point will end up in. We could say that more elegantly. We could say, look at the quadrant of the image and take the signs that are appropriate for that particular quadrant. Okay, we're going to use the signs that are appropriate for that particular quadrant. Let me give you an example. Let's say I wanted to rotate, that is the worst set of X and Y axes I've ever drawn. Not really, but it ranks up there. Let's say I wanted to rotate the point 2, -5, I don't know, let's say 270 degrees counterclockwise, about the origin. Now, and I'm not doing this graphically, I just was giving you that visual. Okay? Now, 270 says they're going to trade places 3 times, because that's 3 times 90 degrees. And for every 90 degrees rotated, the numerical values trade places. So the first time they trade, the 5 would be first. Okay? Let's look at it this way. It's like, here are my numerical values. If they trade, now the 5 is first, trade back the second time, and trade again. So they're going to be the opposite. 5 comes first, 2 comes second. Opposite order. So I've got a 5 first and a 2 second. And then I just look at it visually and figure out where this would get me. Now remember, every quadrant is 90 degrees. So if I rotate 270 degrees, I've rotated through 3 quadrants. Okay, so 1, that's wrong way, isn't it? I just went clockwise, sorry. 1, 2, 3. So I'm going to end up in the 3rd quadrant. What are the signs of points that are in the 3rd quadrant? Well, you have to go left, which is negative for X, and you have to go down, which is negative for Y, to get there. The signs for the 3rd quadrant are negative, negative, so I just make this negative, negative. So there's my answer. Okay, let's do another one. Let's suppose, let's actually go clockwise this time. Let's suppose I have a point, -3, 1. And I want to rotate it 180 degrees clockwise. CW would be clockwise. Okay, 180 degrees is 90 times 2. So I trade them and then trade them back. So in other words, it's going to be 3 and 1. In other words, we trade for the first 90, and it would be the 1 would come first, but then we trade again, so the 3 comes first again. Next is 180 is 2 90-degree turns, or 2 quarter turns. If I'm going clockwise, it's this way. There's 1, there's 2. I end up in the 4th quadrant, and the signs in the 4th quadrant are positive, negative. So there's my answer. If you understand how to use that, that can help you figure out the rules if you ever forget them. All you have to do is treat the original point, pretend that XY is in the 1st quadrant, and you could use those rules to figure out what the formula would be for where it ends up. Okay? Let me just show you that. Let's say XY, 1st quadrant. Let's suppose that I want to rotate it 90 degrees counterclockwise, or just 90 degrees. For every 90 that I go, they trade places. If I'm only going 90, then they're going to be traded. If I go 90 counterclockwise from the 1st quadrant, I'm in the 2nd quadrant. What are the signs for the 2nd quadrant? Negative, positive. And we have the exact same thing that we have here. So you can use that method to figure out the rule if you forget it. And I have done that before. All right, let's go ahead and get through the rest of the problems on this page so that you guys can do your own practice. Triangle STW with point S at 2, -1, point T at 5, 1, and point W at 3, 3, rotated 90 degrees counterclockwise about the origin. Okay. What are they asking me? Oh, they're showing me where it ends up, and they're asking me to just give them the coordinates. Well, that's kind of, they did a lot of that for me, didn't they? We could do more than that, couldn't we? But that's okay. They are telling me that we start at 2, -1. Actually, I have no idea what they're asking me here. Let me just pause and look at this a little bit, because they're giving me all the information I need, aren't they? Maybe I accidentally printed out the key? Hang on. Okay, I figured out what they were looking for. They just want me to put the rule. In other words, which one of these applies. Okay. So we did 90 degrees counterclockwise. That rule is, that's the one, remember I messed up at first. This. Okay. So we started out with 2, -1. It became 1, 2. And the y was negative to begin, so now it's positive. The y changes signs. It doesn't become negative, it changes signs. I'll let you go ahead and figure out those two, because that's pretty straightforward. Okay, so hopefully you got, let's see, 180. You should have gotten this, -x, -y. Looks like my pen is about to run out. Good timing, huh? And for 270 counterclockwise, we should get y, oops, sorry, comma, -x. Okay, before I let you free to do the next page on your own, I do want to point something out here, and actually I could point it out right up here. Let's go up here. Well, how do you use these rules, which are specifically made for counterclockwise situations? How do you use them if you're supposed to rotate clockwise? Well, we already talked about the fact that 180, it's the same no matter which way you turn. You'll get to the same place. So if you're asked to rotate 180 clockwise, you can use this rule exactly as it is. What about 90 or 270? Well, that basically comes from recognizing that if I go 90 degrees in one direction in terms of turning, if I went 90, 180, 270 in the other direction, I'd get to the same place. So a quarter turn counterclockwise is the same as 3/4 of a turn, or 270 degrees clockwise. And the same thing happens down here. If I turn 3/4 turns, 3/4 of a turn, counterclockwise, which is what's happening right here. This is counterclockwise. And that is as well. Everything that's shown here is counterclockwise. That's the same as just rotating 1/4 of a turn clockwise. So we can use that knowledge to be able to apply these rules to clockwise rotations as well. All right, so next up it says examples in your turn. So go ahead and try these. All right, and then I'm going to try to provide you with the chance to check your answers on this. And if you don't have access to a key, you can always compare with a friend and see how it goes. Always remember that if you are transforming a figure, like a triangle, do 1 point at a time. You can go ahead and graph the whole triangle, the whole pre-image, the starting triangle, but when you do the rotation, just take 1 point at a time and do just that point and figure out where it ends up. Then do just the next point and wait until you've done all the points before you connect them and try to make a figure. Don't try to rotate the figure as one, because that's where things go awry. I hope this has helped you a lot, and I will see you later. Thanks for being here.